Mehmet Cengiz Onbaşlı from Koç University, from Electrical and Electronic Engineering, also from Research Center for Translational Medicine. Good. He received his BS from Bilkent University, again Electrical and Electronic Engineering, and did his PhD at MIT, Material Science and Engineering Department. He was a research scientist at Corning, and he's now at Koç University. He will talk about materials and devices for integrated topological quantum spintronics.
Thank you very much for the kind introduction. So I'm going to actually connect with Professor Özgür Müstecaplıoğlu's quantum thermodynamics talk from this morning, and I'm also going to address some of the challenges raised in the previous talk, especially the fidelity problems. For instance, when we have power dissipation problems, one can actually reduce the fidelity, and there needs to be a solution to addressing each of these logic gates. So I'm going to talk about materials and device aspects for these systems from an experimental point of view. So I'm an electrical engineer and a material scientist. So I have been doing experiments, but recently I have been doing also modeling, device modeling for addressing qubit states using spin waves and topologically protected skyrmion states, which could be on the order of 65 kBT energy cost per skyrmion at room temperature, which could help actually improve the fidelities for integrated microwave qubit systems. So let me skip this part because the introduction already covered it. So I'm going to first talk about what the room temperature hybrid quantum spintronic systems really consist of. I'm actually trying to lay out a vision here that consists of a microwave and spintronic systems for quantum computation at room temperature. So for room temperature operation, one needs significant energy barriers that stabilize the qubit states, and the coherence channels must be suppressed quite significantly. So, it all boils down to the magic comes from the materials, and on top of that we need to, of course, engineer the diamond systems for all electrical write-in and all electrical readout. So a hybrid system, of course, needs to consist of an addressing electronics, which I'm not going to cover here, but I'm going to lay out some microwave addressing experimental results towards the second half of the presentation. And I'm going to lay out some of the challenges, especially into all electrical room temperature quantum spintronic processors. You may have seen this figure in the literature. Essentially, all quantum systems consist of either an LC oscillator that drives a superconducting circuit, or microwave resonators that drive a trapped ion system, as you heard in the previous talk, or there could be integrated photonic circuits that could also be doing quantum computation, as you may have seen in the literature. And there are also optical fiber systems that could retain and propagate signals over long distances. So they have their own advantages and disadvantages in terms of coherence time and excitation frequencies. And these excitation frequencies are rather characteristic. And when it comes to spin, spin actually embodies a lot of new physics, because you can engineer the Hamiltonian with a range of different terms like magnetoelastic terms. You can add strain into the material. You can add spin-orbit coupling, which actually breaks the symmetry in the electronic band structure by applying magnetic field and using heterostructures like we are going to show in a minute. So what we are going to cover here today in this presentation is going to be rather in this area, where we are going to have the electronic spin ensembles coming from the spin bus line. So I'm going to be talking about a magnetic layer that acts as a spin bus line, which is addressed using a microwave coplanar waveguide structure. On top of that, we are going to have NV centers, either their nuclear or electronic spins that would process or store information. So, the nice thing is that using spintronic systems allows us to actually address a wide range of frequencies by changing the spintronic state from ferromagnetic to antiferromagnetic. When it comes to antiferromagnetic, one can stabilize the spin waves as skyrmions, circular spin structures, that could help address the NV spin states using exchange coupling or other higher order terms. And by using antiferromagnetic skyrmions, one can actually scale the addressing frequencies towards terahertz regimes, because those are the typical characteristic frequencies of carriers for antiferromagnetic skyrmions. So when we think about the media for storing information at room temperature, we can think about diamond NV systems, diamond silicon vacancies, diamond germanium vacancies, and silicon carbide based systems. So it turns out that all these systems are interesting because of their wide band gap. So the wide band gap allows for reduced phonon density of states, and reduced density of phonon density of states allows for a rather long spin coherence time because the decoherence channels are rather suppressed. In this way, actually, once you have very narrow line widths, it allows for addressing many qubits in parallel at different frequency bands. I'm thinking from a perspective of electrical engineer, where you actually encode information in different frequency bands and engineer the strains of NV centers, or basically lump different frequency bands in different channels. So this is the kind of perspective that an electrical engineer can bring to the table, I think. On top of that, the emission fraction into zero phonon lines are not terrible. And the nice thing is they are all in visible or near visible. So this allows for integration with telecommunication channels as well. So here we can see the photoluminescence as a function of wavelength for NV center in bulk diamond. So the zero phonon line, the emission at which there's zero phonon density of states hits this wavelength. And the nice thing is that one can engineer the phonon density of states in the proximity of this peak using a cavity. The cavity actually suppresses the rest of the decoherence channels, and it allows for a very clean, highly focused peak that improves the signal-to-noise ratio that one can read from readout. And it also enhances the lifetime of spin qubits, actually. So this kind of a mechanism can actually be quite useful for integrated hybrid spintronic and quantum systems. So that's why I will be referring to this kind of an architecture later, as I'm going to discuss the experimental results. So why are we trying to use spintronics on top of quantum systems together with NV systems? So one can always use microwave systems for driving NV in diamond or silicon carbide based defect systems. So the nice thing is that spintronic systems can allow for instance, let's talk about this magnetic layer, which is called Yttrium iron garnet. So this Yttrium iron garnet is a magnetic insulator that has extremely low damping. So that means when you excite spin waves, the oscillations that are occurring within this thin film is causing significant either spin hole voltages or some spin torques that could apply onto the spin states into the NV center. So that's one thing. The other thing is that we could use microwaves to drive this frequency, drive the oscillation frequencies at ferromagnetic resonance. So in the morning we had Professor Ceyhun Buğtay's talk about optical readout of NMR. Here I'm going to talk about optical readout and electrical readout of FMR. So that could be another complement to ferromagnetic resonance-based readout of such a system. So these are basically the memory elements or the qubit logic elements. And then we could simply use the underlayer as the bus line. So since it is an insulator, it eliminates most of ohmic dissipations, which could be a problem for fidelity figures. And on top of that, if one substitutes the ion here, yttrium, with, for instance, terbium, it allows for achieving compensated ferromagnetism, which means you are observing antiferromagnetic spin waves within the structure. And it could allow for actually propagating spins at terahertz rates, which could allow for access to magnetoelastic and voltage-based piezoelectric control of spin wave addressing. So this could be a potential pathway for all electric readout, and that's one of the mechanisms that we have been exploring. So one can certainly construct a system Hamiltonian for such a system here. I'm actually working on this with Professor Müstecaplıoğlu about the system Hamiltonian. So we construct a exchange Hamiltonian here, and one can certainly add many more terms, including the Zeeman term. And once we do a Holstein-Primakov transformation, we actually end up with a harmonic oscillator behavior for adjacent spins, which allows for which governs the interactions between the spin bath and the work that we are trying to extract from this bath. Okay, so. This is one of the ways that we are trying to model the system. So we need to have a Magnon reservoir model. So what does a reservoir look like? We have a range of frequencies that are supported, either eigenmodes or ferromagnetic resonance peaks. And we are going to work with a system that is perpendicularly magnetized. So in this case, when I'm talking about yttrium, iron, garnet, we can substitute, for instance, this with thulium or europium or terbium with other rare earths to end up with a perpendicular version of this, which could allow for stronger interaction with the upper layer. And then we could write the bath Hamiltonian, and the Hamiltonian will need to have these square terms, higher order terms, which could arise due to either spin orbit coupling, magnetoelastic coupling, which could help drive the coupling from here to here. So this could be controlled on demand by either applying voltage or turning it off. So basically, we are talking about spin oscillations within the bus, but we are also talking about the exchange interaction that is driving the behavior. So what?
Where is the NV center here?
Let me show it to you now, actually. So the oscillations are basically in the bus channel right now here, and the bus channel behaves here like this. And I'm going to show some results here related to a previous study that is similar to, that resembles the geometry that we have here. So we have a diamond nano beam here, and there are two NV centers. So in this nano beam structure, we are talking about either coupling these two NV centers using dipolar fields without spin waves, or using spin waves to couple NV centers that would not otherwise couple. So we could use ferromagnetic resonance to basically tune or detune the energy levels within the NV system. So that's one of the ways we have been going through. So the gold contact here is the coplanar waveguide part, and let me continue with the rate equations here. So there are, of course, probabilities of NV spin states to be in the either positive, negative, or zero spin states. So one can come up with these rate equations and measure them experimentally using photoluminescence signal. And essentially, the rate equations boil down to the Rayleigh-Jeans distribution times the density of states of the NV center's energy filter behavior. So we are talking about the coupling strength essentially that drives the transition rates, and that's driven by the NV center's depth from the surface, and it's also driven by the spin density of states inside the magnetic layer. So on top of that, what we are going through is a simplification here is the magnon spectral density. So we could think about the magnon spectral density as either a cavity, just as I showed here. So if you can think about a magnon cavity that could have a defect in the center, and if you reduce the density of states to only one single state, a defect state, in that case you could end up with a single delta function that could be tuned by voltage or a deliberate ferromagnetic resonance that could drive let me show you, a coupling term here that could be selectively or voltage controlled. Okay, so in this picture, I rely heavily on the materials picture because the magic comes from the materials plus the device architecture. So that's why we really have to do a very good job in the materials growth and characterization. And it really boils down to the epitaxy methods that we have been working on for the past 8 or 9 years. And essentially, we can grow monolayers. So I have set up a pulse laser deposition system at Koç. And I'm also planning to install a molecular beam epitaxy system for 2D layers for enhancing the spin orbit torque efficiencies into the magnetic layers using 2D layers on top of garnets. And after that, we're also planning to so the fact that one can characterize in atomic scale with EDX, with analytical chemical like XPS, if we can map, for instance, the atomic distributions in almost sub-nanometer or even close to sub-angstrom resolutions, so that allows for a significant precision into our iterative growth technology. So the important thing here is we believe there needs to be an iterative approach for engineering the materials. On top of that, engineering the device performance. The reason why we focus on these spintronic materials from a fundamental standpoint is that it allows for using new thermal properties. For instance, spin-Seebeck effect could be engineered through different spin hole contacts, and topological properties can be investigated in these systems through the symmetry breaking when you have another top layer like the diamond, strained diamond. And I'm going to talk about, for instance, injecting, propagating, and detecting these systems. So in Spintronics, of course, we are using microwaves. Just as in the previous talk. So the microwave frequencies are mostly on, within the 2 till 20 gigahertz, but there's no fundamental limit to how much one can use. So, but the important thing is having extremely sharp resonance peaks, like a few tens of or 10 or 20 megahertz resonance peaks that could actually match that of the NV center's ESR, electron spin resonance. So once you match those frequencies, we could actually match from the magnon to the NV spin state. And that's what I'm going to show you in a couple of minutes. And of course, this is from a classical standpoint, one can of course construct XOR, XNOR gates, but those are very power inefficient, and that doesn't use the quantum computing scalability either. So that's actually back in 2015, and there are lots of issues with those as well. And interferometers, for instance, could function as a classical gate, but in a quantum system, interferometry delivers much wider output space. That's why we believe these systems could actually be used in quantum systems. So let me talk a little more about Garnet here. So the most important key property of Garnet is that it has low damping. So what does low damping mean? Spins actually propagate within this material, and since there is low damping, it actually gets rather absorbed a long way into the chip. Okay, so it's like optical absorption equivalent of spintronics. Since spins are not absorbed along the way as much as in metallic layers, you can actually propagate across millimeters or even up to centimeters within a chip. So this was known since Second World War II, since it was used in microwave circulators. But the problem is integrating them with chips was a challenge. And once we have solved this problem, it actually became pretty feasible to apply into quantum systems. Let me show you some data about how thickness dependence is actually not very important, and these could be grown on chip rather with narrow line widths. We are talking about 10 megahertz line widths, and the damping is on the order of 10 to the -4, a few 10 to the -4. And on top of that, we are talking about a band, wide frequency band, which could be useful for microwave radar applications as well. And this could also be scaled towards higher frequencies once the addressing microwave electronics and impedance matching is solved. So that's a big challenge though. So once you substitute yttrium with thulium, you can actually still contain a insulating layer, but we change this time the magnetic orientation from in plane to out of plane. What does that mean? I'm basically talking about having the spin waves propagate like this in YIG, and in thulium iron garnet in the second column, I'm talking about the oscillations in this way. So they are in a different orientation. And it actually changes the coupling strength between the diamond NV and the underlayer. Okay, so that's why the chemistry matters in terms of how we can enhance the strength of these layers, the interaction between these layers. So, on the left-hand side, what we are looking at is basically the MOC hysteresis data. MOC is magnetooptical Kerr effect. What we are doing is we grew a thulium iron garnet film on a crystal substrate and applied magnetic field perpendicular to the surface. And after that, what we did was we measured the Kerr rotation of light. So we sent light and then measured the polarization rotation of the light, which is MOC signal. and swept the magnetic field intensity and direction. What we see here is we have some remnant state, which indicates that in absence of magnetic field, we can stabilize magnetism within this chip. So it helps reorient magnetism by itself spontaneously. So we have some vibrating sample magnetometry data. So these are both at room temperature, by the way. And it allows for stable magnetism at room temperature in these insulating low damping layers. So on top of that, the spin hole cross measurement was done to understand how the resistance changes as a function of applied magnetic field. So we are basically currently applying a current along this x-axis. What happens is that we first apply a current, and that current causes an Ørsted field. So the Ørsted field causes a tilt of the magnetism inside the layer like this. And on top of that, there's also a spin torque effect that is generated because of the platinum and thulium iron garnet interface. So platinum has a high it's a heavy metal, so the spin orbit coupling in platinum is large, which means the charge currents passing through platinum is converted into spin currents, and those spin currents are diffusing into the thulium iron garnet layer, which applies torque onto the thulium iron garnet spins, and by sweeping the magnetic field intensity, it turns out that the magnetic orientation within this layer could be switched from spin up to spin down states. So how does this help us? It helps us basically use current to address or change the orientation. On top of that, one can also even lift this field, external field altogether using built-in bias schemes. For instance, if we have a magnetic layer that is a permanent magnet, and it could be like an exchange bias, and we could simply cause a switch between that spin valve layer. So here I'm switching gears towards an application of YIG to YIG on diamond NV systems. So let me switch gears and then be a little faster. What we are doing here is basically we collaborated with the Ameria Kobi group when I was a grad student, and on top of that we basically used the ferromagnetic resonance of the spin waves propagating within the YIG layer to address the photoluminescence of the NV states. So essentially, I would like to show you this plot. What we are seeing here is we swept the external magnetic field on the bilayer that we have YIG and diamond system with the NV layers, and then swept the external magnetic field, and then basically swept the microwave drive frequency, and then recorded the photoluminescence of the sample using scanning photoluminescence microscope. What we see here is basically a Zeeman splitting, obviously, as you mentioned in your talk. But we also have, on top of that, a ferromagnetic resonance. And the ferromagnetic resonance is basically just one state here, because I grew the film so thin that only one ferromagnetic resonance state is supported in this case. That's why we only allow the transition between ferromagnetic state to ESR 0 to -1. So the line widths are on the order of 8 megahertz, and those are very sharp dips. And I'm going to be rather quick because we don't have much time left. So there's another way to actually pump and probe this kind of a system. But this time we are actually trying to use electrical writing and an optical readout. And what we did was, so we first optical writing, microwave drive, and a microwave readout using ferromagnetic resonance again. A similar case happens here. The Zeeman splitting with magnetic field causes splitting of the NV states, and we have a ferromagnetic resonance state that is degenerate with this MS 0 to -1 and back and forth states. So the important thing here is we first initialize the states with green laser here, and then we bring a NV center that is close to the diamond nanobeam here. And then the state inside the NV is initialized with green laser, and then we drive with the microwaves to shift the polarization of the NV by pi over 2, and then at the FMR frequency we read out the transmission. Well, so what does this tell us? We are trying to basically observe if this opening and if the shift within the NV center can perturb an even or odd spin wave eigenmode. So it can be used as a sensor for quantum sensing as well. And what I would like to show you here is basically we had swept external magnetic field and applied a DC current, a DC spin current, and then read out the FMR transmission and photoluminescence for even or and odd spin transfer modes here, basically. Okay, so I would like to continue with this topological protections case, because let me tell you one thing here. These states are on the order of like less than 1 micron wide, so these NV states. The problem with these NV states is that they are so small that we need to actually focus our spin waves onto these layers. And the next thing that we need is actually a focused spin wave structure. So that's why we constructed a spin wave generator structure that could come up with a periodic pulse pattern that could focus down to 20 nanometers or 50 nanometers. And the nice thing about this structure is that we can tune the addressing frequency from a few hundred megahertz up to 20 gigahertz. So we can span 7 octaves of frequencies to basically hold or write or read the NV state. So let me show you the slow case for this low current driving regime. And this is the slow case, and the next one is the faster case. So we see these are the spin states that are down with respect to a initially up polarized bus channel. And what we are planning to do is basically place the NV centers on top of these layers to address them. So instead of having trapped ions, what we envision is having a completely all solid state structure that is integrated, and we would like to operate it at room temperature. So we calculated the energy cost of generating each of these skyrmions, and it turns out 65 kBT at room temperature. But the problem is these preliminary simulations were done with cobalt platinum multi-layers. So it takes a lot of joule heating. So what we are thinking of is substituting these with 2D layers, which could reduce the current consumption by at least 3 or 4 orders of magnitude, and eliminate the dissipation problem for enhancing fidelities for addressing NV states efficiently at room temperature. So one can drive with here high current densities. So these are very large current densities, but the key metric here that determines the performance is the material damping. So if we can tune the damping of the material, we could simply span between like 100 megahertz up to 22 gigahertz for this kind of a addressing scheme. So the important thing is that using voltage injection, damping can be enhanced or suppressed. So these mechanisms were also established previously. So, but let me switch and end with the last bit. So to be able to apply this kind of a system for NV magnon coupled system, we need to address the decoherence problem. We need to address the entanglement problem on chip. So there are already many examples from, for instance, Fedor Yedesko's papers. You can see NV systems coupled just by microwave drive lines without even magnons or anything. And that's with arbitrary waveform generators. But here, what we are thinking of is the drive line is still going to be used. But if we could have those topological rings or circles for spin waves, that could help enhance the coherence times and reduce the power consumption for addressing these spin waves. And on top of that, to be able to solve the addressing problem, we need to enhance the NV magnon coupling. And there are some emerging solutions that were previously proposed very recently. And so people have proposed another multi-layer structure where we have a piezoelectric structure. So the piezo is driven by voltage. And then on top of that, we have a magnetic layer, which is magnetoelastic nickel. And the coupling of the piezo layer with the magnetoelastic layer causes a shift in the ferromagnetic resonance frequency. And that could be read out from the microwave transmission pattern. But the shift in the energy states of the NV's diamond states on top of the magnet are also read out from the pump probe system in the scanning confocal microscope system. So this kind of an addressing scheme can help drive the system turn into a all-electric writing and all-electric readout. But of course, challenges are still there. Like how do we initialize, how do we achieve arbitrary phase initialization. To be able to do that, we need to have a 3D field generation on chip. And that kind of a structure can be basically constructed using a microwave drive line or some kind of a Earth state field generator right next to the qubit. But that has its own challenges in terms of engineering as well. So with that, thank you for your attention.
Okay. So questions? I have a question related to terminal-based Garnet.
Yes.
In this case, probably you will have larger spin orbital coupling, so decay, right? So the speed wave should be larger. What do you think about this?
So the question is, for terbium iron garnet, spin orbit coupling will be larger, right?
Yeah.
And
in this case, how can I say, spin, the coherence length, length in the space units will be much smaller.
Okay, so we could basically suppress or enhance the spin orbit coupling by controlling the magnetic orientation of the layer, the magnetic layer, because the symmetry of the material allows us to basically couple or decouple the coupling of the NV spins. If you, for instance, orient the magnetic layer spin this way and the other NV state this way, the spin orbit coupling will essentially be reduced significantly with respect to the other orientation. So the symmetries and the strain of the layer is also coming into the picture, because there is an in-plane strain, there is out-of-plane strain that kicks in, and that could also be another lever that we could use for controlling. Yes?
why I'm asking about this, because in Yttrium higher garnets, we have very small line.
Line widths, right.
What about terbium densities?
For terbium, they are larger. That's for sure. The problem is that when you have larger line widths, the efficiency of spin injection into NV is going to decrease. But that could be engineered by patterning the garnet layers. So if there's an intrinsic limitation coming from the material, extrinsic methods could help eliminate those issues to some extent.
I would like to make a comment with the table where you are citing coherence time of the various centers. If I know there is silicon vacancy center which has very long coherence times up to 45 seconds, something like this one.
Which one? This one?
It is not silicon vacancy minus, it is silicon vacancy 0 center.
Silicon, it is silicon vacancy minus.
Yeah. So, because if you cite just diamond silicon vacancy in this case, maybe you can cite also various types of vacancies.
Yes, so I should have actually included that because the reference, the authors already mentioned that explicitly in the paper, so I should have written that. But that's okay, so you can understand, but that makes a difference, true.
Question. So, as I understand it correctly, so you have yig and then you have a diamond
On top, yes.
right? And then the yig is, of course, it's an insulator.
Insulator.
You have spin waves. I mean, you basically have magnets, so that allows you to carry spin current.
Right.
So now, what about diamond? I mean, how does it interact with the NV center in the diamond?
You mean,
What is the coupling?
what's the coupling between yig and diamond?
Not the diamond, but the NV center.
NV center. So it is mostly exchange coupling because they are so in such a proximity. The most important interaction term is exchange.
Really? I think it should be dipolar.
Dipolar? Why?
Because you have not the electrical contact between ferromagnetic and spin center in the NV center.
Okay, we are talking about like deep, shallow layers that are on the order of 20 nanometers or less, up to 100 nanometers or less. So there's exchange, dipolar, and we are talking about strain terms coming in from the diamond as well.
So you're saying that the wave functions decay enough overlap with the nitrogen.
So we have multiple NV centers distributed inside. So they could act either as a ensemble or individual cases. But what you are saying is exchange can only happen within just close proximity, right next to each other. So that's true. So in that case, within a few unit cells, of course, yes. And dipolar is also coming into the picture, but in our model, we are only taking into consideration exchange.
Model something else.
Yeah.
Model something. Model, but the real
Okay.
coupling is,
Okay.
you know, it's
Yeah.
you know, there is no real electron
Yeah.
that has to move between the
Yeah.
yig and the diamond to get you based proximity effect, right?
Yes. So that's so the dipolar field definitely comes into play. So I don't discount that. And there's also charge in this picture as well. Yep.
Why? Because we can increase the efficiency of micro-excitation for NV center. Because it is shown maybe one or two, the last 1 or 2 years, that it is possible to increase intensity of microwave excitation of the NV center using Yttrium iron garnet 100 times. And this system are very interesting, which thank you for this excellent presentation.
And for this work which Cengiz is doing, this kind of structure can be used also to control quantum sensors based on MB and also latencies.
Yep.
So,
Thank you. Thank you.